The purpose of this is to go through some of the calculations you're going to do in the measurements lab post-lab. So the first thing I wanted to do is explain what some of these readings are. In the very beginning, you were asked to determine the values of the markings on each of the 4 devices. And the real reason for that was that you needed to be able to read the device to actually measure 9 milliliters. So the correct value should have been 9 milliliters, but how many decimal places we can trust depends on the markings on the device. So for instance, in the 100 milliliter graduate, each marking was worth 1, which meant that each uncertain mark was worth 0.1. And so we can trust this measurement correctly to 1 decimal places because that's what matches the device we used. By the same idea, we had 0.5 for every mark, which means 0.05 for the uncertainty, which means that now I have 2 decimal places in my correct value. In the 10 mil graduate, 0.2 for every mark and 0.02 for the uncertainty again gives us 2 decimal places. Now if you read the beaker correctly, you'll notice that there were, in most cases, one big gap between the numbers
worth 10 milliliters, which means that the most we can trust is to the nearest 1. And so for that device, 9 was the correct value. We'll come back to that correct value in a few minutes. So what I want to do next is look at some basic statistical calculations that we do when we collect data. Let's say, for instance, that my measurements collected using the 25 mil graduate were these 3 values. And of course we know that these are milliliters according to that device. And in fact we know that they were all read to the nearest 0.02 because at the point where we recorded these numbers, we actually had been emptying it into a 10 mil graduate to make these readings. And so that's why the uncertainty matches whatever the 10 mil graduate is, because we filled each of these devices, but we emptied it into a 10 mil graduate to make our recorded measurements. So the first thing you're asked to do is to calculate an average. And the formula for average is you're going to sum all of your data. When we talk about data, we usually call it X, or we use the symbol X. So this could be called X sub 1 because it's X for trial 1, X sub 2, X sub 3. So in our average, we sum our X values and divide by the number of data points. So N is the number of trials, in this case 3. So I'm going to need to sum these 3 numbers, 8.52, 8.48, 8.96, and then I'm going to divide by 3. We'll come back to our calculations in a few minutes here. The next setup is our percent error. The percent error compares what we got to what it should have been. So percent error is calculated by first calculating the bias. The bias is the difference between what you got, your average, and what it should have been, which was the correct value. Since the data I'm talking about in my sample is the 25 mil data, then I'm going to use this as my correct value. So the bias was my average compared to the true value divided by the true, and because this is a percentage, we're going to have to multiply by 100. In my instance, again, because I'm talking about the 25 mil data delivered from the 25, I should have expected 9.00. And so I'm going to have 9.00 for both places here times 100. Now when we talk about percent error, what we're trying to say is how accurate is my calculation.
because accuracy means how close is it to being correct. The next calculation we use is to look at whether or not the device was a good choice in the first place. And so percent relative error says compare what the equipment says you should be able to get. So big U is the equipment tolerance, or the uncertainty. And we're going to divide that by the measurement you were trying to make. In this case, this would be then the true value that you're trying to make. And then we're going to multiply it by 100 to make it into a percentage. So notice that the percent relative error entirely comes from the true value. That the true value is 9 to some number of decimal places. Again, since we're talking about the 25 mil data, we're going to be looking at 9.00 as my true value. And the uncertainty on that device was 0.05. And so what this allows us to say is, if we use the equipment to the best that it is marked, to the best of what the manufacturer suggests, this much data error is going to exist. This is how much error we can blame on the equipment. And if we have a high value of percent relative error, it means we probably shouldn't use that equipment, that the amount of error associated with the equipment compared to the measurement you're trying to make is just too large. An example of this might be if I used a yardstick to measure the width of a hair. The amount of error in the yardstick is huge compared to the length or the width of my hair. And so that would be a terrible device, and it would give me a very large percent relative error. Now, before we can calculate the last one, we have to be able to calculate our deviation. Deviation says what kind of individual variations are there within the individual data points. And so your deviation is calculated for each trial. It's going to be calculated as your value, I'll just call x sub n, whatever your trial number is, compared to the average, because theoretically they should all pretty much average to the same value, or it should be all very close to each other. But we can see that this number, for instance, is very different than the other two. And so deviation helps us to zoom in on which data point may not be as trustworthy as others. Now, because we're looking at amount of difference, we don't really care whether it's too high or too low. We just care that it's different. Same thing's true about percent error. In many cases, all we care is that it's just not right. And so we're only going to be looking at bias as a function of how large a difference it is. So we're going to use the absolute value, which means that no matter what our actual numbers are, we have to end up with a positive result, because we're just...
And so we're going to do the same thing here with our deviations. We're going to take the absolute value. So we're going to need to take a second and actually calculate our average. Give me just a second, I'll pull up my calculator. So when I substitute in the numbers for the first one, I get 8.52, clear that, 8.52 plus 8.48 plus 8.96 gives me a total of 25.96. We're dividing that by exactly 3. And I get 8.653333 ad nauseum. Now, in terms of sig figs, the rules about sig figs say when we add numbers, we only care about their decimal places. Both of these, or all three of these rather, have 2 decimal places. So when I sum them,
I can trust both decimal places in my sum. So just this portion of my operation gave me 4 sig figs in my numerator. Now the other rule of sig fig that applies here is that if we're talking about an exact number, you can't have half a piece of data. You can't have half a child if you're calculating the average number of children. And so there are as many decimal places as you want in an exact number. And so this value has infinite sig figs. So when I do this division, the division rule says I don't care about decimal places, I just want to know how many sig figs there are. So this numerator has 4 sig figs, our denominator has only infinite sig figs, and so I can trust this number to 4 sig figs, which is why then I subscripted these last. Now sometimes people will put an X over the last ones just to show that they're not valid. Sometimes you'll see them in parentheses so that you know that those numbers are not valid. But since we're not done with all of our calculations, we don't want to round yet. So let's look a little farther here. Now that we know our average, we can set that up and calculate our percent error. Our average was 8.653 sub 33. Carry a couple extra. 2 extra sig figs without rounding is plenty and won't introduce extra error into our calculation. So I'm taking 8.6533, I'm going to subtract 9.00, and I get a value that's absolute as 0.346666 whatever. Since again I'm subtracting, subtraction is all about decimal places. This number had 3 good decimal places. This one had only 2 good decimal places, so we can only trust in our calculation 2 of those digits. Since we're not done yet, then we're not going to round yet. So that's our subtraction. We still have to divide by 9.00 and multiply by 100. Now that I'm multiplying and dividing, the sig fig rule says that I care about how many sig figs total. So the numerator has 2 sig figs, our denominator has 3 sig figs, and since the 100 is part of a definition, it's considered exact. So our answer should have 2 sig figs. And when I did that, I came out with a very small error. Let me check my math here because I don't trust it. There we go. I came out with 3.851. Since I'm at the end of the road here, 3.9%. Now it's appropriate to round. Percent relative error, let's go ahead and calculate that while we're here. 0.05 divided by 9.00 times 100, and I got 0.5555. Since this number is only good to 1 sig fig, then I can only trust 1 sig fig here. So 0.6% relative error. Since we are doing ratios here, the uncertainty would have been in milliliters, the true value would also have been in milliliters, so the percentage problems don't usually have units. The percentage is the unit of that problem. So now we're ready to look at deviations, and as I mentioned before, the deviation is calculated for each trial. And so for trial 1, that would be my value, 8.52, minus the average 8.653. Carry a couple extra sig figs because I'm not yet done. For the second trial, 8.48 minus 8.653 sub 33, and 8.96 minus 8.65333. So again, deviation is calculated for each trial. Since it's an absolute value, this cannot be a negative number. 0.13, because we're subtracting, it's about decimal places. I've got 2 decimal places, 3 decimal places. I'm only entitled to 2 decimal places. Since I'm not yet done, I'm going to carry a couple extra. So now I've calculated my deviations for each individual trial. I'm ready to calculate my average deviation. So again, I'm setting it up. Absolute value of one of the trials here, 8.52 minus 8.653 sub 33, gave me 0.1333 as my deviation. Which brings me finally to percent rad. Percent rad stands for relative average deviation. Deviation says how much variation is there in the individual trial. What we're going to look now is at how much variation there is on average. So what we're going to do is we're going to find our average deviation. Now last time when we talked about averages, we used the symbol X bar, or X with a line over the top. And that bar means that that's an average. And when we calculated the average, we summed the values and divided by the number of trials. We're going to do exactly the same thing. We're going to calculate the sum of our deviations over the number of our trials. In this case, 0.013, alright, that's a typo, 0.1333 plus 0.1730 plus 0.3067, and again we had 3 trials, so n is 3. Since I'm first summing, I look at decimal places. And I came out with a total of 61. Since I only have 2 decimal places, I'm going to subscript the next 2, 297 or 30. Again, I'm carrying just a few extra. I need to still divide by 3 to find my average. I came out with 0.2043 because now I have 2 sig figs and infinite sig figs. Again, when I multiply or divide, it cares about sig figs. When I added, we care about decimal places. And all of them had 2 decimal places. So our answer when we added was only to 2 decimal places. So now we have our average deviation. We're ready to calculate our percent relative average deviation. And that's going to be d bar over x bar times 100. So we're going to take our average deviation divide by our average value and multiply by 100. And I came out with, a percent relative average deviation of 2.36%. Now let's check our sig figs. We had 2 sig figs here and 4 sig figs here, infinite because 100 is part of a definition of percentage, and so I'm entitled only to 2 sig figs. This is 2.4%. Big picture, deviation talks about how reproducible your numbers are. So relative average deviation tells us about precision. Ideally, we want a low deviation. We want a low percent deviation. So the higher this gets, the poorer our procedure. Percent relative error talks about whether or not the equipment is a good choice. And percent error tells us about whether or not our equipment is reading the right numbers. Now, ideally, we would like our percent error and our percent red to be smaller than our percent relative error. Since I just made these numbers up, I made no effort to make good numbers. And so if you can say that your percent error and your percent relative average deviation are smaller than the percent relative error, then pretty much you can blame it on the equipment. You did what you were supposed to do and you got a reasonable answer. The percent error in part is just to check to see that the equipment you're working with is calibrated correctly. And so you're looking at whether or not, assuming you're using it properly, the equipment gave you the right value. Percent rad says even if the equipment's marked wrong, your numbers should be close. These numbers are not
very small numbers. It means that you're not very good at doing the same thing more than once. And so that's what these calculations are about, and I hope this helps.